As part of Space Week Cambridge, we have curated an online magazine on the theme of potential of lunar and Martian settlement, with select interviews with pioneers and experts in the field of astrobiology, aeronautical engineering, and space law. Through our interviews, we try to understand the complex environment of the moon and Mars and explore what it truly takes to send a successful crewed human mission to both these celestial bodies in order to create a permanent human settlement. No human has visited the moon since the end of the Apollo program in 1973. However, this is about to change with the US, ESA, Russia, China, and India proposing to send manned missions to the moon. They are accompanied by ambitious private sector firms who are recruiting settler candidates for the Mars mission. Our journey to these celestial bodies will be faced by different challenges and questions. Can these planets support human life? What does it take to create a successful human settlement? Is it going to be a rebirth of civilization on these celestial bodies? Would humankind carry forward their baggage from Earth to the celestial bodies, or would we aspire to be better? And if we do, who is going to hold us accountable to these lofty standards? Come join us as we talk about robotic versus human explorers, the design and architecture of lunar habitats, and the effort it takes to bring together several national space organizations to work together on a feat never attempted before.
That many scientists do think that space and planetary surfaces can be explored with robots. Although I disagree with that. Well, obviously they can be explored with robots, but it just comes down to which is the most efficient way of exploring planetary surfaces. I think if we compare the efficiency of things like the Apollo expeditions to the moon 50 years ago, and then compare those to the efficiency that we're currently exploring Mars with these little rovers, then there is no comparison. The Apollo astronauts were orders of magnitude more efficient as explorers than these little rovers on Mars, and I can say more about that later to justify that assertion. But I do think we've got to be a little bit careful. There is a difference between the moon and Mars. It's true, I think ultimately both places will benefit from having human explorers. But it is quite important that we get how to phrase it. I think I'll just backtrack a little bit. On Mars, we've got to be very conscious of the fact that we know one of the things we want to learn about Mars is whether Mars has any life of its own or has had any life of its own. It is therefore very important that we don't contaminate Mars with Earth life until we have an answer to that question. So although I am an advocate of human space exploration, I think we should hold off a little bit on human exploration of Mars until we have learned quite a bit more about the Martian environment, and in particular whether Mars has any life of its own, using robotic space vehicles which we sterilize before we send them to Mars. Now the moon is different. There's no risk of contaminating moon life with Earth life because the moon will be a totally uninhabitable environment. So the way I see this is I think we should be exploring Mars for the next few decades. We should be content to explore Mars with sterilized robotic space vehicles like Perseverance and Curiosity and all the others, because we can learn about the Martian environment without contaminating the Martian environment until we have an answer to this very important question as to whether there's any current life on the surface of Mars. I mean, there probably isn't, but nevertheless, I think we should be sure. But while we're doing that over the next few decades, we have the capability to build up a robust human spaceflight capability on the moon, such that when we're ready to go to Mars, when we judge it safe or responsible to send people to Mars, we will then have a human space flight capability, human space exploration capability that we've developed on the moon that will stand us in good stead for sending humans to Mars in due course. So I'm not one of those, I mean, I do think we will learn a lot more about Mars when we send people there. I stand by my statement that human explorers are going to be much more efficient than robotic explorers, but I still think we have to be a little bit patient. We still have to learn quite a bit more about Mars before it would be responsible to send people there. Whereas the moon, we can use the moon to practice human operations on a planetary surface, and at the same time learn a great deal about the moon, which will also be scientifically very, very interesting. So I think the key scientific benefit of humans as explorers is their versatility and their flexibility and their innate intelligence that at least contemporary robots don't have. So I can illustrate this by comparing the way the Apollo astronauts explored the moon 50 years ago and the way we're currently exploring Mars. And bear in mind, we're exploring Mars with robots that are 50 years more advanced robotically than anything that existed in the 1960s. So already the robots have a head start, you might think. And yet in terms of efficiency, I can still argue that the exploration of the moon by the Apollo astronauts was much more efficient than the exploration of Mars with rovers like Perseverance or Curiosity or Spirit and Opportunity. So Steve Squires was the principal investigator for the Mars exploration rover Spirit and Opportunity. And in his book, Braving Mars, where he describes his experiences with that mission, he reflects on the efficiency of his robots on Mars. And so bear in mind, he's the principal investigator of a robotic Mars mission. But he writes this in his book. He says, the unfortunate truth is that most of the things that our rovers can do in a perfect day on Mars, a human explorer could do in less than a minute. And this is true from a geology point of view. I mean, it takes hours and hours for the rovers to position themselves up to a rock, take the photographs of the rock, deploy their scientific instruments to try and measure the composition of the rock. A human geologist, even encumbered in a spacesuit, would take 30 seconds to pick this rock up, look at it under a magnifying glass, classify it, decide whether it was important or not, and if necessary, put it in a cache to be studied more carefully later on. So a human geologist would make those decisions, as Squires said, in less than a minute, while these rovers have been spending a day. I mean, that would be a good day, gently positioning themselves around this rock, trying to deploy their robotic instruments.
One of the things NASA, for example, and others really would like to do with the first settlement on the moon and our development of technologies and structures for the lunar surface is that it have a capability to satisfy our needs on Mars as well. So we don't have to redevelop everything. Now, there have to be differences because the environments are quite different, both deadly, but different as well. So as far as the moon, coming to it as an engineer, the first thing engineers do when they design a product or anything is they define the environment that product has to go into. Like, is it going to be very hot, very cold, vacuum, no vacuum, gravity, all the things. So for the moon, what a structural engineer will have to figure out is how to deal with the radiation effects on the moon, which are deadly, how to deal, as we know, the moon has 2 weeks of daylight, 2 weeks of nighttime, very cold to very hot for 2 weeks at a time. You have micrometeorites hitting the surface of the moon continually. You even have lunar seismic events, which people don't really realize. The moon has moonquakes, and so they're not really very serious for the most part. But if your structure is at the location where a moonquake happens, it may not be very severe, but it lasts for very long periods of time. And so things like antennas and things could be damaged severely. So all these things coming together have to be taken care of. And the other thing that an Earth-based structural engineer doesn't have to deal with usually is life support, because we have air around us and everything is fine. But if we're on the moon, that structure is contained. It's almost like a submarine, right? The submarine, everything is in that submarine, and it's pressurized, and it's shielding the people inside against the very large pressures from the ocean. On the moon, it's the opposite because it's a vacuum. So the vacuum effects means that your structure has to be sealed and pressurized up to about the same atmospheric pressure we have here on Earth. So that force, that pressure distributed throughout the interior of that lunar base has to be sustained by that structure. So those are all the issues that sort of the structural engineer has to deal with. But because of the fact that these are generally going to be very small structures initially, there are a lot of human factors issues. For example, human psychology, being in close quarters, even figuring out what kind of colors we should have, color schemes. Do we have plants in different locations? The psychology of living in that kind of environment is pretty severe. And people have done studies, including engineers, of how do people live in submarines? How do they live, believe it or not, in prisons? What does that do to your psyche, right? And finally, you have the physiological effects. So the low gravity on the moon, we cannot simulate here on Earth. It's one of the few things we can't test here on Earth. We can sort of do something like with water tanks, but it's not really perfect. And we know from our experience in space and on the space station that humans don't do well in low gravity environments. Even in space, it's almost zero gravity. On the moon, it's 1/6 G. Mars, it's 3/8 G. There is some concern that we just aren't suited for any kind of environment other than 1G, because that's how evolution brought us to this point. That's what we know. That's what our genes know. So there's a lot of research, perhaps using gene therapy, exercising, a whole bunch of different things to keep people healthy over long periods of time. We still don't know how to do that. So that's an issue. And so the structures now have to be able to accommodate all the technologies and things that we need to do for the humans there so they survive as well. And one final environmental thing that I think will be part of a future question that you'll ask is about the regolith on the moon. So the regolith is toxic. It's carcinogenic for humans. We saw from the Apollos that it got blown up and it was a fog on the ground when the rovers drove around. It's electrostatically charged. And so basically it becomes like a fog that just doesn't settle for very long periods of times, and it clings to metals. So that brings challenges from the engineering point of view. How do you build machines with gears and robotics kinds of mechanisms and protect them from that regolith getting into the gears? They saw it on the Apollo, they had real problems with that. And the other side of the coin is that if the astronauts breathe it in, which was an issue during Apollo, it basically is carcinogenic. So the regolith is a real problem, but ironically, the regolith is also something very valuable. So the in situ resource utilization that we've all studied and know how important it is, basically using local resources to build things so you don't have to bring them from Earth where it's expensive to do that, is in the regolith. And the regolith has that value. So it's a valuable commodity, but it's also a dangerous commodity. And so there's a lot of engineering involved in how to use it in a good way and then protect machines and humans from that regolith. We know from psychological studies of humans that certain interior colors make one feel more calm, like certain blues and greens. That's why people like to have plants around them. It just makes them feel very comfortable. And the other thing about the structure for psychological well-being is people don't like, we see many of these space art where the structure is like a tube, like a cylinder. Those aren't very good for humans because basically it's just a narrow view. It's like living in a hallway rather than a room. And so a lot of the later concepts show inflatable structures and large domes just because it gives people that large sense of space. And that's very important for humans. And then of course the colors, I'm not a psychologist, but I've read some of the papers and they say that just the way that you distribute the colors give people a sense of depth and perspective, and also makes them feel like they're not in a very confined space. When we think about settlements on the moon, we think in stages. So the first stage is going to be like a pressure vessel of the kind that we see in the space station. It's going to be built on Earth, orbited, landed. And so the first astronauts are going to be there. It's pioneering high-risk kind of living. Eventually, when we have enough infrastructure on the moon, we're going to start building larger ones. Maybe we'll build very large inflatable structures, very large volumes, and then we may have people there that are really living there permanently. And at that level, stage 2, stage 3, where you're using local resources, you're using 3D printing technologies to build very large habitats, then you're going to have the whole human as part of the design constraint. So it's not just surviving and living and doing tests, but it's also how to live and be able to thrive on the moon, to feel happy on the moon, that you feel like this is home. That may sound a little trite, but I think the reality is, if you're a military person living in a submarine for 6 months, you don't care about the colors. But if you're on the moon permanently, you're essentially in isolation from Earth, where if you think about it, the moon, there's no outdoors on the moon. You're always in something. You're either in your structure or you're in a spacesuit. You're never walking through the fields like you can on Earth. So you're always in a container on the moon. And psychologically, that can be very challenging for most people. They have to probably be trained for that and to survive. So part of the design is, as you said, are people who are not engineers who deal with interior decoration, design, architecture. There's a whole field of space architecture that deals with the engineering plus other aspects of creating a good environment for humans, you know, as human beings rather than as people who do experiments or dig in the ground.
I think one of the fundamental issues about governance, like the rules that the humans on the moon or on Mars will follow, is to what extent does the Earth have an obligation to create the legal rules for people who live on a different planet? So, for example, if there are astronauts going to the moon for 30 days, they go up, let's just say on a US private launch vehicle, they spend 30 days, they come back to Earth. Well, those astronauts are essentially, as you know, the envoys of humankind, but they're also representatives of their nations, right? Certainly that's true for government astronauts. It's a much different situation for private citizens who would go to Mars with no intention of coming back. If they're going to Mars essentially on a one-way trip and they're staying there forever, then why do they need to follow Earth law or US law or Washington, D.C. law? Maybe they should make their own legal rules for their own situation, right? I mean, there's very little that's analogous. Like here on Earth, if you want to step outside and get some fresh air, that's almost like a fundamental human right, the right to go outside and see the sky and breathe the air and drink clean water. That might not be a fundamental human right on Mars. You certainly can't step outside and see the blue sky. You can't go for a swim. You might not even be able to go, drink all the water that you want, right? Maybe bathing will be restricted. Water's not going to be unlimited the way people think about water here on Earth. So there could be very specific reasons that we want the laws on Mars to be very different than the laws here. And I think it's a mistake for us now to think about writing laws for people 100 or 200 or 500 years into the future. I think that if we needed to guess what their lives would be like, we would never guess correctly. And it's not fair to lawyers to ask us to try to anticipate what their lives will be like when even scientists and engineers don't know what it will be like. So how do we write laws for situations that we have trouble imagining? I think that it's premature to try to legislate the future. As we talked about earlier, I think we will never be able to guess accurately what the future will bring. You had Sputnik launch in 1957, and it wasn't until more than a decade later that you had the Outer Space Treaty, and then 12 years later that you had the Moon Agreement. So that's 20 years later. So I think that absolutely what you said, that national legislation will precede international agreements, I think is how it's going to shake out in the future. You know about Article 6 of the Outer Space Treaty and the obligation to authorize and supervise the conduct of a state's nationals. And I think you'll have an individual state, doesn't matter what state it is, but they will make the sovereign determination. You know, states read treaties and determine what those treaties mean for each state. You'll have a state that says such an activity is legal under the Outer Space Treaty or under international law, and they will authorize it. And maybe another state will complain And then maybe a third state will complain, and then maybe states will get together and say, we need to regulate this. We need to come up with some international agreed way of doing things. But you saw that with the Outer Space Treaty and Article 2. You heard Professor Jaku talk about the 2015 US Commercial Space Competitiveness Act. And that was the US unilaterally interpreting what Article 2 meant. And they interpreted it the same way they did back in 1969 to say that we're allowed to use and explore outer space. You're allowed in situ resource utilization. And the US contends that that law will not be exercised in violation of the Outer Space Treaty. It'll just essentially be a continuation of the practice that had existed for at that point, it was 4 decades. So I think you will have individual nation states authorizing activities that get the ball rolling. And when you have a few of those happening, then I think you'll have international movement after that. I agree with the fact that there are responsibilities on them, but I think the answer is pretty simple. Article 3 of the Outer Space Treaty says that activities in outer space need to be done in accordance with international law. So that little phrase of in accordance with international law, I think is the standard that you need to look at, that these early actors, and it could be any of the countries that you named, it could be Russia or China or India or the US, could be other countries that you didn't name. The UAE comes to mind as being very active. European countries are very active in outer space. But as long as they perform their activities in accordance with international law, I think that's probably a pretty good yardstick to start. Now,
to know more about what our experts have to say, please check out the extended versions of all our interviews.